Okay, so we're going to get started with a final exam overview, and this is kind of like the Cliff Notes version of different topics. And I may break this up into a few sets of videos, but this is going to start us off with the most recent stuff. So, as you know, the final exam is going to be 10% of your grade, and 25% of that's going to be electrostatics, and then the rest is what we're really going to focus on. We're going to focus on that 75% of the test that is the old material, so multiple choice and problem solving. One of our most fundamental topics is the concept of magnitude. All right, we've used the term magnitude a lot, and remember that magnitude plus direction is what we call a vector. So this is just the number, and this is up, down, right, left, north, south, east, west. So when you have a combination of a number and a direction, we call that a vector. And so you can think about vectors might be velocity, displacement, force, acceleration, all those things. When we have just magnitude only, so it is just the number, then we have a scalar. And a scalar might be speed, distance, work, energy. Those are some of the scalars that we have talked about this year. So things that I could ask you, obviously I could ask you to solve for work or energy, kinetic or potential, and we'll get to that a little bit later. But we'll focus on the concept of vector first. So I could ask you basically how to draw a vector. And we should know that there are a couple of different parts to this. That the length indicates the magnitude. So when we're looking at how we are setting up our vectors, and we have things that have different magnitudes or different numbers, then we need to draw them different lengths to basically show that different amount. And it needs to be proportional. The head is the direction. So that's very important. And remember, by convention, when we draw our compass, we have north, south, east, west, and our values, when we draw something up, is positive, to the east or right is positive, down or south is a negative, and left, west, negative. Okay, that's important to remember. So I could also ask you, here are different vectors drawn. So here's a vector, and here's a vector, and here's another vector, and here's a little vector here. And I may ask you, well, which one is, which vector has the least amount of magnitude? And you would circle this one, right? Because it's shown to have the smallest line, or the smallest length, and that would indicate that it has the least amount of magnitude out of those. And that's a pretty simple, straightforward question. I might also ask you to be able to draw and interpret a vector diagram, and that's probably the direction I would be going about it. So we need to know about vector diagrams, how to interpret them. Like if I draw one, I might ask you questions about it. And you also need to be able to do this yourself. So if I draw something like this, and I say that the object is in motion, and I have gravity force balanced out with the normal force, right? Because it's not levitating and it's not rising up, so these forces have to be equal. And then I draw in a vector like this, and I label it like that. Remember that Fk is kinetic friction, which is the friction of a moving that exists between a moving object and another surface. Surface could be at rest, surface could also be moving, but there is motion of a surface against another surface. So the object is in motion, it has kinetic friction. So I may ask you to describe, so there are two potential questions here. Describe the type of motion and direction of motion based on just that information. So instead of asking you on a test what the definition of kinetic friction is, which is really boring, right? Why would I ask you that? I might set it up in a diagram like this, in which you have to then use or interpret that information to solve more of a visual depiction of what's going on. So you know by now that friction always opposes motion. It always works against how the object is moving. So I know the direction of the motion has to be against friction. So I know if I were to draw the motion of this particular object, I know that the object is moving in this direction. I know that the direction is, I can say right, because I don't have a compass drawn, but if I had a compass drawn and I said this is east, I could label it as east, right? Or I can just say this direction. Any of those would be correct, okay? The east has to be dependent on the compass that you draw, right? Because right is not always east, okay? So I know the direction. Now I got to figure out the type of motion. So going back to another principle that we talked about, which was the principle of mechanical equilibrium, which I'm going to put on the next page. But if this is the only horizontal force acting on it, I know the motion is this way. The type of motion that is existing here is acceleration, right? So it is accelerating to the right, and acceleration can be speeding up, slowing down, or changing directions. So the type of motion is going to be acceleration. Okay? So let's review, okay, the types of motion. So types of motion. So there are three basic types of motion: rest, constant velocity, and acceleration. So if something is at rest, it's not moving. It is remaining still relative to some point, right? Constant velocity means same speed, same direction. And if I'm accelerating, I can be doing basically one of three things. I can be speeding up, I can slow down, or I can be changing direction only. Of course, I could say, well, I could be speeding up and changing direction. I could be slowing down and changing direction, or I could just be changing direction only. So, you know, you could extend that list out. But these are the three basic ones that we've talked about in class that would be important to remember. Okay. In the case of these two right here, under all circumstances, if you have something that is at rest and you have something that is doing this, there's a special thing that we have talked about in class, and that is mechanical equilibrium. And mechanical equilibrium basically states that the vector sum of the forces is equal to 0, which is a fancy word of saying your F net, which is the sum of all your forces, right? We've used both. They mean the exact same thing. Okay? So anytime you're not moving, so if I were to draw you not moving, I have my gravity force, I have my normal force, and I'm not moving. That is mechanical equilibrium. My F net is 0. If I'm undergoing constant velocity, it means that if I were to draw this out, let me do a different color here. It would mean that my applied force and my friction force are equal. It would also mean that the object was in motion to begin with, right? I have my FG, sort of draw it out, my FN. So in order for this to hold true for mechanical equilibrium and constant velocity here, I would need to state that this was already in motion to begin with. If it's not already in motion, and you should probably understand that it's in motion because I use FK, that's a good tip, but I will probably be even more deliberate in telling you that it is in motion. When you go from rest to some value, you have to accelerate, right? You can't go from rest to some number without accelerating first. But once you have undergone the acceleration, so let's say I accelerate at a red light, so I'm at a red light, I accelerate forward, I go from 0 to 30 miles per hour in, say, 4 seconds. That's my acceleration. But after that 4-second mark, let's say for 10 seconds, I go 30 miles per hour north. So I have a constant velocity during that 10-second time frame, right? And I would draw it looking like the applied force and the force of kinetic friction are equivalent, okay? So these forces are balanced. So I'll put that on under there. Forces are balanced. In order to move an object, right, from rest, I have to unbalance the forces because I'm going to have to accelerate. So acceleration, let me go back to this, can never be in mechanical equilibrium. The F net is always some non-zero number. If you are accelerating, there's always some non-zero number, period. That is just how it is. You can accelerate left, you can accelerate up, you can accelerate right or down. It doesn't really matter. Remember, though, that you will always accelerate in the direction of the net force. Okay? So you will always accelerate in the direction of the net force. So keep that in mind as well. All right. I am going to stop it here and then start a different video so you don't have, if you want to just sort of block out and watch different videos at different times. I'm going to go through the different types of forces and do some vector diagrams on the next one.